Hello, this is Darren McKnight, and I'm privileged to speak to you today about space traffic management, but I really want to focus, instead of on space traffic management or space traffic coordination, making sure we do not build this new space traffic management on a weak foundation. The figure to the left represents what I mean by this weak foundation. Basically, we want to support the development of a trillion-dollar space economy. This obviously is going to be directly supported by new and enhanced space traffic management standards and operations. However, beneath that, there's a foundation of the orbital debris collision risk, which without more stringent debris mitigation guidelines and actually operationalized debris remediation capabilities, it is likely that the debris population may undercut the best and the most professional space traffic management system that anybody can form. Another way of saying this is let's not be penny wise and pound foolish. Space traffic management or space traffic coordination is really very important as we have more satellites going into orbit. We have more businesses that are leveraging the space assets and many new improved space technologies. As a result, space traffic management technology solutions such as collaborative conjunction assessments, better math and measurements to support these conjunction assessments, more complete and faster data sharing. All of these really focusing in on the key thing is we need to avoid collisions between operational satellites. So how do we do that? As far as the space traffic management foundation, I'm going to say it's built on something that I like to call space debris management. And for today, I'm just going to talk about three simple components, three simple actions that I think that we should all take on as requirements moving forward. First, stop launching rocks. Why are we still launching satellites that don't have collision avoidance capability? It's not that hard. There are many examples that we can show where even 1U, 3U CubeSats have done collision avoidance maneuvers and can take and have propulsion systems. And I suggest that any satellite above 400 kilometers should have a propulsive collision avoidance capability. Number two, we should no longer condone leaving derelict hardware on orbit for 25 years. That's many generations of the current satellite systems. It's just an awfully long time. There's no reason for us to litter and put a 25-year rule on how long it's allowed to linger. We should do better than that. Thirdly, we need to start picking up the objects that we've already left. But which objects are the question? So today I'm going to introduce to you this concept of statistically most concerning debris, the large derelicts, and I'll explain how we came up with a list and how those things should go. So why are these three things so important? They're important because they will control the growth of the lethal non-trackable debris. Lethal non-trackable debris is debris that's not cataloged, so it's smaller than 10 centimeters in low Earth orbit, but greater than 5 millimeters because it still can cause mission terminating effects on satellites. 97 to 98% of all mission terminating collision risk actually comes from this lethal non-trackable debris. While most space traffic management systems are looking at avoiding collisions between operational satellites and between trackable objects, in reality, it's going to be this small debris, the lethal non-trackable, that's really posing the greatest risk to future space operations. So let's first take a look at the 25-year rule and how it was established and why it has remained the standard. One of the quotes that came about from looking at these 200-year simulations depicted on the right says reducing the 25-year rule to, for example, a 5-year rule only leads to another 10% reduction over 200 years, which is statistically not significant. So this curve to the right, many of you have probably seen, and NASA's run these simulations where they look at the catalog debris for all of low Earth orbit. So I want to emphasize that. Catalog debris, not lethal, non-trackable, and for all of low Earth orbit. So it means it adds up everything up to 2,000 kilometers. So the interesting thing about that is obviously objects, debris that get created above, say, 1,000 kilometers, 900 kilometers, 1,200 kilometers will linger for hundreds of years. But if it gets generated at 500, 600, 700 kilometers, if a breakup occurs, it won't linger very long. It'll actually go away. So in essence, the 25-year rule, using the metric of the number of cataloged objects after 200 years, doesn't really even consider the altitudes of 850 kilometers or so and below. These breakup events that could occur on a routine basis would not be tracked within this 200-year metric, but at the same time, there would be decades at a time with very high collision probabilities of both trackable and lethal non-trackable that would greatly curtail space operations. In essence, the 25-year rule is a very valuable rule to prevent environmental stability. And again, this plot represents sort of that focus on the environmental stability. Many people look at that as the cascading effect from the Kessler syndrome. However, space safety really is important to look at collision probabilities wherever the operational satellites are, which is below 850 kilometers, many of them. And also you need to look at the lethal non-trackable debris. And so the criteria used to select the 25-year rule and support why we shouldn't change it really doesn't have space safety as its primary concern. Another aspect of the 25-year rule can be shown here in this plot is that the newly deployed satellites that will have their operation altitude below 650 kilometers allows them to not require any sort of post-mission disposal plan because atmospheric drag will move it fine on its own. So that's great. So lots of new satellites, as represented by this green line on this curve, are being launched below 650 kilometers. One, it's not very high altitude. Number two, you don't have a lot of the debris mitigation guidelines being imposed on them. However, at the same time, massive derelicts, non-operational payloads, or abandoned rocket bodies, spent rocket stages, once they are finished being used, maybe above 650 kilometers, even below, if they are moved below 650 kilometers, then that means they are also compliant. Unfortunately, that combination of the green line for the operational satellites and the red line here shown for the risk from the massive derelicts. This is not spatial density of all objects. This is only showing objects greater than 700 kilograms with the red curve. So what you see is just to the left of the compliant line, you start to see this unfortunate overlap of many new operational satellites and many derelict objects. The red humps that are to the right of the not compliant line, the higher altitudes, represent some clusters of derelict objects that I've been modeling and characterizing for years. The vast majority of that debris, over 80%, was deposited before the year 2000. This is a remnant of before the debris mitigation guidelines. However, the humps to the left of the compliant line are much newer. Many of those objects are actually deployed after 2000. So this trend of more operational satellites being layered on top of more massive derelicts is not something that looks like it's going to be good for space safety. However, any collision that occurs between those objects will not show up on the 200-year simulation of trackable objects because they'll be washed out quickly on the scale of 200 years, but not quickly enough if it's 10, 20 years, even 30 years on orbit, because that's going to affect all of these new operational satellites. Let's take a little closer look at post-mission disposal thresholds. So this plot shows where the 25-year rule is, about 650 kilometers, and the curves here are provided by Christophe Bonal and Luciano Anselmo from a paper that they did, and it shows the spatial density of all cataloged objects in 2000, 2010, and 2020. And what it shows is where a lot of the debris has increased, and as I hinted at earlier, with the green line to the left of the 650 kilometer, the 25-year rule, there's a significant increase in new objects there. And this green line will contain both operational and dead things. And so what's often talked about is that PMD reliability is more important than the threshold. We need to get the reliability up before we change the threshold. However, if you look at where the 25-year rule line is, 650 kilometers, basically the fact that PMD reliability is important is just really a function of drag effect. And by the way, of course it's important. It needs to be very important. But if it was a lower altitude, like a 5-year rule or a 1-year rule, then the PMD reliability is still important. So let's show you where the 1-year and 5-year rules are. So this now depicts a 1-year rule about 400 kilometers, the 5-year rule being about 500 kilometers. So in essence, if you can move everything to 400 kilometers, it naturally decay within about a year for an intact object, roughly. And so what's interesting about this is, as you remember, I stated earlier, I think that every object above 400 kilometers, every satellite should have propulsive collision avoidance capability. So now what this would mean is it's basically anything that's going to be in orbit more than a year on its own needs to have responsible behavior. It should be able to avoid a collision if it gets in a close encounter with another object. So how difficult is it? Now that we have propulsive capability on board, if we satisfy this requirement of collision avoidance capability, how hard is it to move objects from higher altitudes to this new 5-year or 1-year rule altitude? This table that I just added shows the impulse required to move objects from as high as 1,500 kilometers to either the 25-year rule, the 5-year rule, or the 1-year rule. The question we have to ask ourselves, how good is good enough as far as the efficiency in making those maneuvers? So to do that, I want to go back to the source. Debris mitigation guidelines as established in the mid-90s were some very forward-looking guidelines, and much of the format that was put out by NASA originally in that and then propagated through IADC, United Nations, through CNES, through many other organizations have really stood up to the test of time. And in one of those early reviews by Reynolds, Eichler, and Johnson, I'm sure you recognize those 3 names, they talked about the establishing of the 25-year rule, and then they talked very specifically about why you cannot ask satellites to adhere to a more stringent PMD threshold. And they said, quote, typical propellant requirement for 25-year lifetime to meet the 25-year PMD threshold is 2 to 5% of the dry mass of the upper stage. And so in essence, we can't ask for them to do more than that. Well, that makes perfect sense. And in the 1990s, that made sense. So the question now is, have technologies changed? This chart is a chart that was coming out of in a paper that I worked with 2 real rocket scientists from Aerojet Rocketdyne, where what we basically did was we looked at 3 types of propulsion systems on the lower legend here: monopropellant, bipropellant, and electric thrusters. We applied those 3 different propulsion system types to 3 families of satellites, as we have here in the title of this chart: 15 kilogram 6U CubeSat, 300 kilogram smallsat, or a 2,000 kilogram class satellite. And we applied it looking at altitudes of 1,500 kilometers, 1,000, 800, and 650. And for all of these, looked at the mass fraction for moving a satellite, those 3 types of satellites, using those 3 types of propulsion systems from those altitudes all the way down to adhere to the 1-year rule. And this line now represents the 2 to 5% mass fraction as stated by the early standard bearers for the debris mitigation guidelines. And what it shows is that electric thrusters provides this capability to meet those established thresholds that we shouldn't cross in the 1990s. Now we're able to find a 1-year rule for the same requirement that before only allowed us to have a 25-year rule. So some of you have heard me say before, our debris mitigation guidelines have not kept pace with space technology. This is exactly what I mean by that. Electric thrusters now provides that capability to meet that anecdotal threshold. We can't be burdensome on satellite designers and manufacturers. So, in summary, space traffic management or space traffic coordination is an enabler, not the objective. The objective, as we talked about earlier, is reliable space operations for all, which really means that we need to be able to reduce the L&T collision risk, the lethal non-trackable risk, now 200 years from now is really important number looking at environment stability. It is not relevant for ongoing space safety of the systems that will be supporting this trillion-dollar space economy. So if we want reliable space operations to stand up, we cannot let debris mitigation be poor, the guidelines not be stringent enough, not be responsible enough, and we need to make sure debris remediation starts now. A one-legged stool is not going to stand up. We need to have propulsive collision avoidance capabilities for all satellites above 400 kilometers. I'll digress for a moment here. The space station's around 400 kilometers. I don't think that it makes good sense for the International Space Station to be at the bottom of basically graveyard orbits that we've establishing by a 25-year rule. A one-year rule would establish that graveyard below the space station. That seems to me to be much more logical in the long run. Secondly, do a 5-year or 1-year rule for the PMD threshold. As I mentioned before, if we establish that all satellites being deployed have a propulsive capability, the amount of mass fraction that would allow us to adhere to a 1-year rule over a 25-year rule meets that 2 to 5% mass fraction penalty that was highlighted in 1997 is why we couldn't do anything more stringent for 25 years. Now we can. Please, if you're interested, I'll send you a copy of the paper that I just finished doing with Aerojet Rocketdyne to show all the actual numbers. Lastly, let's pick up our trash. There are many things that were deposited before mitigation guidelines were put in place. As we mentioned many times before, the majority of the mass of derelict objects in low Earth orbit were deposited before the year 2000. So last year at the IAC 2019 in Washington, D.C., somebody asked the question during one of the sessions, does somebody have a list of the objects that need to be removed first? I stood up, raised my hand, and volunteered to put together a team. And what we've done is we've executed with 19 scientists from 8 countries, organizations around the world, to develop 11 separate algorithms to come up with 11 separate top 50 lists of the top 50 statistically most concerning based upon probability of collision, consequence of collision, and a number of other topics that are outlined in the paper. And then we combine them all together for the composite list for what objects need to be remediated in low Earth orbit first. This paper has just been completed. So what hopefully you got from today's discussion is that while space traffic management is vitally important, if we build it on a weak foundation of poor space debris management, then the collision avoidance, which is the crux of space traffic management, is going to be complicated and going to maybe even be made irrelevant if we don't manage the space debris population, especially the lethal non-trackable debris below that. I thank you for your time. I know having a virtual workshop like this is sometimes very difficult, so I'll now open the floor for questions. However, I already did get one question. Somebody asked me, what have I been doing during this pandemic? What I've been doing is going to the beach a little bit more, spending a lot more time with my new granddaughter, Lily, and also catching up on some hobbies. So, are there any other questions? Thank you for your time.